Asteroids were the rocky, airless remnants from the early formation of the solar system, objects that had been present since the planets coalesced from the protoplanetary disk approximately 4.6 billion years ago, and that had never been incorporated into a planet. Their material preserved in essentially its original chemical state across the entire history of the solar system as the most primitive available record of the conditions that had existed before any planet existed. Here is every type of asteroid, explained in full. Let's break this down. C-type asteroid, carbonaceous. C-type asteroids were the most common type of asteroid in the solar system by a significant margin, forming the majority in the solar system and making up almost 75% of all known asteroids. 3/4 of the entire asteroid population belonging to a single compositional class whose specific physical properties communicated something profound about the chemical state of the outer solar system at the time the planets were forming. More than 3/4 of known asteroids belong to the carbonaceous, carbon-rich C group. Objects that were very dark and mostly made of carbon, thought to be the most ancient asteroids in the solar system, reflecting the very materials that had existed when the solar system first formed before any geological processing had altered the primordial chemical mixture. C-type asteroids had an albedo, the fraction of incoming light they reflected, of only 0.03 to 0.09, making them among the darkest objects in the solar system and explaining why they had not been detected in more remote regions of the outer solar system, despite being the most common compositional type. They reflected so little light that the most distant C-type asteroids were effectively invisible to conventional telescopic surveys. The most famous examples of C-type asteroids were Ceres, explored by the Dawn spacecraft from 2014 to 2018, revealing a world with bright salt deposits in its craters that communicated the presence of liquid water in the asteroid's past. And 1955 Bennu, the target of NASA's OSIRIS-REx mission that collected a sample from Bennu's surface in October 2020 and returned that sample to Earth in September 2023. The OSIRIS-REx mission's return of a sample from Bennu was the most scientifically significant asteroid investigation in history. The 121 6-gram sample of Bennu's surface material being analyzed in laboratories worldwide and revealing a composition rich in carbon compounds, hydrated minerals, and organic molecules, including the amino acid building blocks of proteins, communicating that C-type asteroids, like Bennu, were the solar system's most important reservoirs of the complex organic chemistry that was likely transported to the early Earth through impacts, and that may have contributed to the origin of life. C-type asteroids were mostly found at the outer edge of the main asteroid belt, their increasing abundance with distance from the Sun reflecting the temperature gradient of the protoplanetary disk in which they formed, the outer disk being cool enough to preserve the volatile bearing minerals and carbon-rich compounds that characterized the C-type composition, while the inner disk's higher temperatures had driven off those volatiles from the asteroids that formed there. The 2F-53 Matilde asteroid, visited by the Near-Shoemaker spacecraft in 1997, demonstrated another remarkable property of C-type asteroids: its extremely low density of approximately 1.3 grams per cubic centimeter, less than half the density of solid rock, communicating that the asteroid was not a coherent solid object but a porous rubble pile with a significant fraction of empty space within its interior, a structure that had profound implications for understanding how large impacts affected these ancient objects. Hit the like and subscribe button to see more videos like this. Leave a comment on your favorite type of asteroid. Let's get back into the video. S-type asteroid, siliceous. S-type asteroids were the second most abundant compositional class in the solar system, contributing almost 20% of all known asteroids and forming the dominant population of the inner main belt. The portion of the asteroid belt closest to the Sun, where the higher temperatures of the protoplanetary disk during solar system formation had driven off the volatile-rich minerals that characterized the more distant C-type population, leaving behind the silicate-rich rocky compositions that the S designation communicated. S-type asteroids were mainly composed of silicates, hence the letter S standing for siliceous. Being a moderately bright type of asteroid believed to be composed largely of silicate minerals, including olivine and pyroxene, along with metal-bearing minerals that gave them a higher albedo than the dark C-type asteroids. S-class asteroids were quite common in the inner part of the main asteroid belt their proportion decreasing at greater distances from the Sun. The gradient being the direct compositional signature of the protoplanetary disk's temperature structure, the inner belt's higher formation temperatures producing rocks dominated by high-temperature silicate minerals, while the outer belt's lower temperatures preserve lower temperature carbonaceous and hydrated mineral compositions. The albedo of S-type asteroids ranged from 0.1 N to 0.28, significantly higher than the C-type's 0.03 to 0.09, making them considerably brighter in reflected sunlight and therefore easier to detect at greater distances, which had contributed to the historical overestimation of S-types relative to C-types before surveys specifically designed to detect faint objects corrected the census. The most scientifically studied S-type asteroid was 433 Eros, the first asteroid in history where a spacecraft landed, the Near-Shoemaker probe touching down on Eros' surface on February 12, 2001, after spending approximately 1 year in orbit around the asteroid and conducting the most comprehensive characterization of a single asteroid that had been performed up to that point. Eros had dimensions of approximately 34 by 11 by 11 kilometers and was a contact binary, 2 lobes joined at a narrow neck, whose irregular shape communicated the violent collisional history that had reshaped it from its original post-accretionary form. The Hayabusa 2 mission's visit to the S-type asteroid Wungstine 2173 Ryugu brought back the first asteroid sample from an S-type body in 2020, and the laboratory analysis of the Ryugu samples revealed hydrated silicates and organic compounds that were not expected in an S-type body based on telescopic spectral observations, communicating that the surface and interior compositions of S-type asteroids were not as simple as the spectral classification had suggested, and that the spectral taxonomy captured only the surface properties rather than the full compositional picture. M-type asteroid, metallic. M-type asteroids occupied the middle of the main asteroid belt and represented the solar system's most extraordinary potential resource, objects composed primarily of metallic iron and nickel, whose specific origin as the exposed cores of once differentiated bodies made them the remnants of a violent period of planetary formation during which collisions between larger protoplanetary bodies had shattered them and scattered their metallic cores as individual asteroids. Located in the middle of the main belt, most M-type asteroids were thought to consist of metals like nickel and iron. This latter type could be fragments of larger bodies that once had liquid cores before they were shattered in collisions long ago. The differentiation process that had produced the original parent bodies of M-type asteroids was the same process that had produced Earth's iron core. When a body grew large enough for its interior to melt, the denser metal sank toward the center while the less dense silicate rock floated to the surface, creating a layered body with a metallic core and a rocky mantle and crust. When two such differentiated bodies collided violently, the collision could shatter both objects and scatter their layers as separate populations of asteroid fragments, the rocky mantle fragments becoming the siliceous S-type asteroids, the basaltic crust fragments becoming the V-type asteroids associated with the large asteroid Vesta, and the metallic core fragments becoming the M-type asteroids. The most studied M-type asteroid was 16 Psyche, a large metallic asteroid approximately 226 kilometers in diameter, whose composition of predominantly iron and nickel communicated that it was the exposed metal core of a protoplanetary body that had been stripped of its silicate mantle by ancient catastrophic collisions. NASA's Psyche mission launched in October 2023 and was en route to the asteroid as of 2025, with an arrival expected in August 2029. The mission's scientific objectives being to characterize Psyche's composition, geology, and internal structure with instruments designed to answer the fundamental question of whether Psyche was indeed a stripped planetary core or a more compositionally complex body whose metallic appearance reflected a different formation history. Main Belt Asteroid. Main Belt asteroids were the most numerous population of asteroids in the solar system by raw count. The asteroids residing in the vast region between the orbits of Mars and Jupiter, known as the main asteroid belt, occupying the space from approximately 2 to 3.5 astronomical units from the Sun, in a region whose total mass was estimated at approximately 3% of Earth's moon, despite containing millions of individual bodies. The asteroid belt itself occupied the area between Mars and Jupiter, the area where Jupiter's gravitational interference had prevented the material from accreting into a planet, the specific resonances between Jupiter's orbital period and the orbital periods of asteroid belt objects at specific distances, creating regions of gravitational instability called Kirkwood gaps that were largely devoid of asteroids, the main belt's internal structure being shaped as much by Jupiter's ongoing gravitational influence as by the original distribution of material during solar system formation. The total population of main belt asteroids larger than 1 kilometer was estimated at approximately 1.1 to 1.9 million objects, with the number of objects smaller than 1 kilometer being effectively uncountable with current survey technology and likely numbering in the hundreds of millions to billions depending on the size distribution assumed. The largest objects in the main belt were no longer classified as asteroids. Ceres, Vesta, Pallas, and Hygeia were sufficiently massive to be classified as dwarf planets or near-dwarf planets, with Ceres being officially classified as a dwarf planet by the International Astronomical Union in 2006. The Dawn spacecraft visited both Vesta and Ceres in sequence, spending 14 months in orbit around Vesta from 2011 to 2012, and then traveling to Ceres, where it orbited from 2015 to 2018, the first spacecraft to orbit 2 extraterrestrial bodies in sequence, providing the most detailed characterization of main belt asteroids larger than approximately 500 kilometers that have been conducted, and revealing Vesta as a compositionally differentiated world with a large impact basin at its south pole, exposing the asteroid's mantle, while Ceres showed evidence of geological activity, including bright deposits of sodium carbonate in impact craters that were among the brightest features on any asteroid surface yet observed. Near-Earth Asteroid. Near-Earth asteroids were the asteroid population of most immediate practical significance to humanity, objects whose orbits brought them into the Earth's orbital neighborhood, creating the possibility of future impacts that range from local devastation to global civilizational threats depending on the size of the impactor, and whose monitoring and characterization had driven the development of planetary defense as one of the most consequential applied fields in modern astronomy. Near-Earth asteroids were also commonly called NEOs, near-Earth objects, and there were currently more than 30,000 detected ones being constantly monitored, as these were the ones that represented the most danger to Earth. For an object to be considered a near-Earth object, the closest point of its orbit to the Sun had to be less than 1.3 astronomical units. The 1.3 AU threshold encompassing all objects whose orbits brought them close enough to Earth's orbit that impact was physically possible over the time frames of solar system dynamics. Near-Earth asteroids were further divided into subtypes based on their orbital characteristics relative to Earth's orbit. Amor asteroids had orbits that approached but did not cross Earth's orbit. Apollo asteroids had orbits that crossed Earth's orbit and had orbital periods of more than 1 year. A10 asteroids had orbits that crossed Earth's orbit with orbital periods of less than 1 year. And Atira asteroids had orbits entirely inside Earth's orbit. The most publicized near-Earth asteroid of recent years was 90942 Apophis, a 375-meter diameter S-type asteroid that had been calculated in 2004 to have a 2.7% probability of impacting Earth in 2029, the first time any asteroid had ever been assigned a significant impact probability. Before additional observations ruled out the 2029 impact, but identified a close flyby on April 13, 2029, during which Apophis would pass within approximately 31,000 kilometers of Earth's surface, closer than the geostationary satellites that provided Earth's telecommunications. NASA's DART mission, the Double Asteroid Redirection Test, launched in November 2021 and impacting the asteroid Dimorphos in September 2022, demonstrated for the first time in history that a spacecraft impact could measurably alter an asteroid's orbit, reducing Dimorphos' orbital period around its parent asteroid Didymos by approximately 33 minutes, and proving that the kinetic impactor technique was a viable planetary defense strategy for asteroids given sufficient warning time. Trojan asteroid. Trojan asteroids were asteroids that shared an orbital path with a planet but remained stable in their orbits by clustering around specific gravitational equilibrium points, the Lagrange points L4 and L5, that lay approximately 60 degrees ahead of and 60 degrees behind the planet in its orbit. The gravitational balance at these points between the Sun, the planet, and the asteroid, creating a configuration that was dynamically stable over extremely long timescales. The Jupiter-Trojans formed the most significant population of Trojan asteroids, and it was thought that they were as numerous as the asteroids in the main asteroid belt, estimates suggesting the Jupiter-Trojan population contained as many as 1 million objects larger than 1 kilometer in diameter, making it a second asteroid belt whose total mass was comparable to the main belt. The Jupiter-Trojans were divided into two groups, the Greeks clustered at L4, leading Jupiter in its orbit, and the Trojans clustered at L5, trailing Jupiter, the naming convention having been established before all the objects at L4 were recognized to have non-Trojan names, resulting in the Trojan asteroid Patroclus being embedded among the Greek asteroids, and the Greek asteroid Hector being embedded among the Trojan asteroids, the two exceptions remaining as historical anomalies. The Lucy mission, launched by NASA in October 2021 and in the early stages of its 12-year journey as of 2025, was the first spacecraft designed specifically to visit Jupiter-Trojan asteroids, with a planned itinerary of 7 Trojan asteroids representing the most diverse single-mission asteroid tour in NASA history, and the first direct investigation of bodies that have been recognized as scientifically fundamental for over a century. The Trojan asteroids were compositionally dominated by D-type and P-type asteroids, primitive, very dark objects with extremely red spectral slopes that communicated compositions different from the main belt's C-type and S-type populations, suggesting that the Trojan asteroids had formed in the distant outer solar system and been captured into their current Jupiter-associated orbits during the dynamical rearrangement of the giant planets early in solar system history. Rubble pile asteroid. Rubble pile asteroids were one of the most counterintuitive concepts in planetary science. The idea that some of the solar system's most ancient and most structurally coherent appearing objects were not solid rocks, but loose aggregations of countless smaller fragments held together only by gravity, their interiors being more similar to a pile of gravel than to a solid boulder. The structure of a rubble pile asteroid communicated a specific and violent history. The original solid asteroid had been shattered by a catastrophic impact. The fragments had not dispersed entirely because they had insufficient velocity to escape each other's mutual gravity, and the fragments had gradually reaccumulated under gravity into a single aggregate body whose overall shape might look solid from the outside, but whose interior was a porous, loosely bound collection of diverse-sized fragments, with significant void space between them. The OSIRIS-REx mission's investigation of Bennu provided the most dramatic direct evidence for rubble pile structure. When the spacecraft briefly touched the asteroid's surface to collect its sample, it sank 24 to 48 centimeters into the surface before the sample collection system's nitrogen gas forced the material into the collector, the surface behaving more like a liquid than a solid and communicating that the surface layer was an extremely loosely consolidated granular material with almost no cohesion between particles. Ryugu, Hayabusa 2's target, also showed characteristics consistent with a rubble pile structure, its top spinning shape being consistent with rapid rotation having redistributed material from the poles toward the equatorial bulge, a redistribution that required the material to be loosely consolidated rather than structurally rigid. The rubble pile structure had profound implications for planetary defense. A kinetic impactor designed to deflect a solid monolithic asteroid would behave very differently when striking a rubble pile, the porous interior absorbing much of the impact's momentum rather than transmitting it efficiently through the body, meaning that rubble pile deflection might require different techniques than the kinetic impactor method proven effective against Dimorphos.